So I'm going to show the console workflow via example called the titanium microresistor actuator. This is not a fluid flow related problem, but it could be. So imagine a bridge-shaped beam that has 2 feet and then a bend. So basically you apply, it's a conductive material, titanium. So when you apply a potential bias across the 2 feet, you're going to have current flow through it. And then because of the current flowing, then you're going to have resistive heating. So the joule heating is going to generate heat. And the entire structure is going to heat up. So there is going to be a temperature gradient in the structure. Because there's temperature gradient, then it causes thermal stress. So this entire structure is actually going to deform because of all that. The problem definition here, we have the first physics, which is the electric currents simulation, DC current through conductive media. And the second physics is the thermal conduction with the joule heating as the heat source. So it's a purely conductive problem. So the boundary condition will be setting will be we'll glue the 2 feet on a huge heat sink, so the temperature remains unchanged to 93.15. And then for the rest of the surfaces, we assume they are adjacent to dry air, so they actually subjected to convective cooling. And then the third physics is a solid mechanics problem with the thermal stress. So to make the problem more interesting, you can introduce the reverse coupling very easily, say, through the temperature-dependent material properties. Say the electric conductivity is a function of the local temperature. All right, so I'm going to start console. Here it is. And I'm going to start a new model. So the two options you have on this first interface is you can either start with a blank model or start with a model wizard. So the model wizard is basically the first few steps of defining your model workspace. So I select the model wizard, and now you ask me to select what's the space dimension I want to work with. So of course, in a more theoretical class, you would always start with a more simple situation like a 0D or 1D problem. 0D, you don't have to create a geometry. 1D, you just draw a line with a certain length. And then the other options would be the 1D and 2D axisymmetric. So 1D axisymmetric is essentially equivalent to a 2D circle surface. And then the 2D axisymmetric is equivalent to a 3D in a rotation symmetry way. Both the physics plus the load and the boundary conditions have to be, plus material properties have to be axisymmetric in order to qualify for that. And then there is also the 2D and 3D options. So right now I'm going to choose a 3D. It's a 3D actual beam. And then I'm going to choose the first physics I want to solve for, which is the electric currents, right under the AC/DC folder. So here the physics are grouped not by modules, but by application areas. So I'm going to choose add. There's a little specification on what is the interface and what it does. It's going to solve for a capital case V, the electric potential, and I can move to the study node. In this case, I'll choose the simplest, the stationary as the solver type. Click on done. So now the model wizard finishes task. Now you're in the main console graphical user interface. We call this the GUI. So in the GUI, you see I'm using a Windows system, so the screen now gets divided into a few parts. If you use a Mac or a Linux, you'll see a slightly variant of this interface. Instead of this console ribbon, we call the console ribbon and tabs on the very top, you would have a console toolbar, so a slightly condensed version of it. And then basically on the ribbon, you have the different tabs that goes from definition to geometry to material, physics, mesh, study, and results. So that's the workflow I'm talking about from left to right. And the same thing here in the model builder, you have an inverted tree structure with a root on the top and branches and nodes after it. There are a few options because we dictated that during the model wizard step. But essentially, you go from top to bottom of this tree. You will go from definition, geometry, material, physics, mesh, study to results. So that's the workflow too, from top to bottom of the tree. You can change the sequence in any part of the model. It's just a general guideline that once you have all the steps aligned, you'll eventually have the results. So all the options here are either through the buttons on the ribbon or through the right clicks on the model builder tree. So all the options are through the right click. So when you're in doubt, right click. And in the middle, we have a settings window. So when you click on certain node in the model builder tree, you have the corresponding settings for it. And then in the right, we have a graphics window with many buttons. Now it's a 3D geometry, so it shows the 3D coordinate. And in the very bottom, we have messages, progress, and log. So in this case, we're going to start with building the geometry in console. So I'm going to start with a work plane. So work planes right here. You see there are some 3D primitives, and if you import, there is some CAD defeaturing tools, and there's also the, I want to emphasize the virtual operations. For those of you who have complicated CAD geometries, those would come in very handy. And then after I created a work plane, I essentially added a work plane step under my geometry sequence. And under that work plane 1, now if I see the settings of work plane 1, it's a horizontal plane, which I actually want to change it to a vertical plane, so XZ plane. So under work plane 1, I have a plane geometry. When I click on it, I go into the 2D workspace. I could use the jawline operation to sketch the profile of the beam very quickly. So I do a series of left clicks and then a right click. It forms an enclosed surface. You could change that surface into a closed curve or open curve as well. And you see that each of the points that I click on, the coordinates are documented as a Bezier polygon in the geometry sequence. So everything you do is documented in that model builder tree. And you can change those coordinates if you need to. So this is actually a microbeam, so I'm going to go back to the geometry node before I forget, change the default length unit from meter to micrometer. So now I don't have to type the e to the -6. So now I have a 2D geometry. I can right click on the work plane 1, add a extrude, and I'm going to extrude it for about 0.2 micron. That should be good. So now I have a 3D geometry with a 0.2 micron as the thickness. So now that's the geometry step. I'm going to close the geometry node and move to the next one, which is the materials node. I can right click, choose the first one, add material, and it's going to browse to the console material library. I'm going to choose the built-in. The built-in folder actually comes with the base package, so you always have it. I can right click on the titanium materials, add it to component 1, and close the add material panel here. So now titanium is added to my material list and automatically assigns the properties to all the domains that I have. The first material I pick will be assigned to all the domains. So right now there is only one domain, and now it's going to use 2 of the properties. So those properties are what the physics calls for, and that's because in the physics it's assigned to domain number 1, and the material property says from material. So that's how the geometry node, the material node, and the physics node all tie together. If the material pick actually doesn't have that information necessary, you're going to get a stop sign right here. And when it goes through the solver, it's going to give you an error message saying maths.epsilon_r is missing or something similar to that. So always check the material property. And then the next node is the physics node. So as I said, you always follow the same workflow no matter what kind of physics you work with. So you'll see that essentially the first physics I added has 3 default nodes. You can tell they are the default from the uppercase D on the icon. So the default governing equation, you can tell from the shape of the icon, which is a field cylinder. That means it's on the domain level. So if you see the equations very quickly here, that is the Laplacian type of equation we want to solve for. And that applies to everywhere in the domain. If you right-click on electric currents, you see the other options here. That's other than the current conservation, you also have terminal as the domain, force calculation, and then a list of boundary conditions. So right now, the default boundary conditions is electrically insulated everywhere, so no current goes in or out. N dot J equals to 0. And the initial value, essentially in a stationary problem, that's an initial guess. That is 0 potential everywhere. So we're happy with comparing these equations with the equations we wrote down in the on the slide. We're happy with the governing equations, but we do need to replace some of the boundary conditions. So I can do that by right-click on the electric current physics, add a ground condition, and now I can choose that boundary I want to work with. So the graphics window in console works with a 3-button mouse. You can left-click, rotate the view, right-click, panel the view, click on the center scroll wheel as if it's a button, move up and down, it'll zoom in or out. So with a combination of that, you can very easily navigate to any part of the geometry, and you can always go back to the default view with those default buttons here. So in this case, the ground is going to be applied to one of the feet. So I'm going to rotate and basically expose the foot, and then hover my mouse over, do a single click, So now boundary number 1 is being selected to satisfy the ground condition. If there is actually a very complicated geometry that some surfaces are hidden inside the domain, you could use the transparency option or the wire rendering to have the different visualization. And you can hover your mouse over and then use the center scroll wheel to rotate through the different surfaces, the different layers of the geometry to get to the inside layers. So again, that makes the selection easy. You can also, in the definitions, define some selection list, like everything within this certain ball shape all belongs to one group, and they'll satisfy the same condition through the model, through the entire model, something like that. The other condition I need to change is the electric potential condition on the other foot, and that's going to be 0.2. And now if I go back to electrical insulation, surface number 1 and 10 are both overridden, so they no longer satisfy that n dot j equals to 0. Instead, they satisfy the one with the red triangles that basically tells you what's the correspondence communications between the different nodes. All right, so that's it for the physics. Any questions for the physics?
Could you say more about the red triangle?
Oh, sure. Yeah, so when you click on electrical insulation, ground and electric potential has the upward red triangle, meaning that this condition gets later on overridden by the other two conditions. When you click on the ground, it says that the electric insulation has actually a definition on some boundary conditions on the same boundaries, and it's overridden by the ground. So it means those two nodes are actually defined on the same space, and which one dominates which one. So in terms of a lot of places, the sequence does not matter. For example, if you have 10 different physics, how they are actually sequenced in that component 1, it doesn't matter. The only thing matters between the physics is how you have the communication between them. What's the coupling that's happening between the physics? But the sequence of the boundary conditions do matter, especially if you define unduplicate boundaries. Then the later defined conditions will override the earlier defined ones. Some of the boundary conditions can coexist. For example, natural convection and radiation can coexist on the same surface in heat transfer problems, and some conditions are not coexisting, so the later defined ones will be the one effective.